This section is all about work, and it is an application of integrals. So work, we think about going to work, doing your homework, but in this case, it means force, or the amount of force that it takes to move an object. So in general, we think of the force on an object using Newton's second law of motion, which says that force is equal to mass times acceleration. So how heavy something is multiplied by how fast you're moving it is the force. In the metric system, mass is measured in kilograms, displacement in meters, and time in seconds. The force is newtons, kilograms per, and kilogram times meters per second squared. So 1 Newton acting on a mass of 1 kilogram produces an acceleration of 1 meter per second squared. In U.S. customary system, the fundamental unit chosen for force is to be the pound, and that just includes gravity in there. The case of constant acceleration, then work is just equal to force times distance. If force is measured in newtons and distance in meters, then the unit for work is a Newton meter or a joule. So I'm going to write these things down. So force in metric, our units are newtons. In U.S. customary, and I'll just say U.S., the units for force are pounds. For work, in metric, our units are Newton meters, and Newton meters, or joules. And in US, we just take foot and pound and kind of squish them together and call them foot-pounds. So remember, Newton meters, not Newton centimeters. So when you have metric, you want to use meters. When you have US, you want to use feet, not inch pounds, but foot pounds. So we're going to have to do some converting sometimes. Let's see, if F is measured in pounds and distance in feet is foot pounds, which is about 1.36 joules. I don't expect you to memorize that. So let's start with a really simple example where we have a constant force. How much work is done lifting a 1.2 kilogram, okay, so I have kilogram book off the floor to put it on a desk that is 0.7 meters high, and we use the fact that acceleration due to gravity is 9.8 meters per second squared. So if we look back up here, Newton's law says that force is equal to mass times acceleration. Distance over so here the mass is equal to 1.2 kilograms. The acceleration is acceleration due to gravity, and I'm going to call it G for gravity. It's 9.8 meters per second squared. And we want to know the amount of work that's done, so work is going to be equal to force times distance, which would be 1.2 times 9.8 times the distance is 0.7 meters. And here we have m times g, so 1.2 times 9.8, that's the force, is 11.7 newtons, and then we multiply by the 0.07 meters, which gives us about 8.2 joules. Part B, we have a 20-pound weight being lifted 6 feet off the ground. So force is already included in the pounds. Pounds includes acceleration due to gravity. So force is equal to 6 pounds, 20 pounds, excuse me. So work is just equal to 6 feet times 20 pounds, which is 120 foot-pounds. So pounds includes that acceleration in it already. 120 foot-pounds. So weight is a force. It's not just the mass of the object. There's a difference between weight and mass. How much work is done when a hoist lifts a 200-kilogram rock to a height of 3 meters? Again, the rock isn't changing its force, so force would just be equal to mass times acceleration. So mass is 200 kilograms. Acceleration is 9.8. So let me grab my calculator. I have 200 times 9.8, 1960 newtons, and then work, we take the 1960 newtons times 3 meters. And I get 5880 Newton meters, or I use joules. So, if we have constant force, all is good. All we have to do is multiply. But you know, it's not going to be that easy. If it varies, then we imagine taking a bunch of little slices, adding them up, and seeing how much it takes to move each little slice, finding the sum. And what does that sound like? It sounds like an integral, because we're looking at a summation of the distance, the force, for each x of I times the distance that each one moves. So delta x would be the distance, and f of x of I would be the force. So we take the integral from A to B. Let's look at an example. So a particle is located at a distance x feet from the origin. A force of x squared plus 2x pounds acts on it. How much work is done moving it from x equals 1 to x equals 3? That's a job for an integral. That's this example 2. So work, we're going from 1 to 3. And we're given our force function, x squared plus 2x. Now that's super easy. We know how to do that. Add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, divide by the new exponent. Evaluate from 1 to 3. And yeah, we get 50 over 3. foot-pounds. Practice number 2. So I'm going to take a minute and set this one up. I just wrote down my problem. I'm given a force function, and it is in newtons. So that means my units for my work is going to be joules or newton meters. We're assuming that X is given to us in meters. So work is going to be the integral for the first one there, from 1 to 2 cosine of pi x over 3 dx. So I'm going to use my calculator for this, turn it on. Don't know why I have that on there, but we're going to clear it off. Do second integral from 1 to 2 cosine, be sure you're in radian mode, pi x, so pi x over 3. Close the cosine of parentheses. So integral from 1 to 2 cosine of pi x over 3 dx. And I get an answer 0. 0 work. That doesn't seem right, does it? Let's see what happens as we move it from 1 to 1.5. I'm going to be lazy. I'm just going to come up here and change that 2 to 1.5. Oh, there is a number there. It's 0.128. Now, it wouldn't be that hard for us to do this by hand, but we're going to use our calculator. Let's see what the work from 1.5 to 2 is. Make a prediction. What do you think it's going to be? So I'm going to change this, delete, delete, back to 2, and I'll change this one to 1.5. It's negative 0.128, because what does cosine do? It oscillates. So it has moved up and it has moved back down, so it has undone the work that it did. That happens. Next important thing we need to know is Hooke's law. There's always a Hooke's law question on your test. Hooke's law talks about springs. So it states that the force required to maintain a spring stretched x units is proportional to x. So force is equal to K times X. K is called your force constant or spring constant. It depends upon how heavy duty the spring is. So if you're given the force, you can figure out your spring constant. If you're given the spring constant, you can figure out the force. As long as you don't go too far and stretch that spring so much that you've destroyed it. So example 3, a force of 40 newtons is required to hold a spring that has been stretched from its natural length of 10 centimeters to a length of 15 centimeters. Centimeters. Remember what newtons are. Newtons deal in meters. Joules deal in meters. So we need to convert this to meters. So force, and we have a distance here. We go from our natural length of 10 centimeters to 15 centimeters. So that is 0.1 meter to 0.15 meters. So we've stretched it 0.05 meters is equal to 0.05 times our spring constant, which is equal to 40, because 40 newtons. So I can figure out that my spring constant is equal to 40 divided by 0.05, which is 800. We want to know how much work is done stretching the spring from 15 centimeters to 18 centimeters. So its natural length was 10 centimeters. We're going from being stretched 5 centimeters to being stretched 8 centimeters. Let me get my decimal point in the right place. 0.08. 800 x dx. And now that one's super easy to find the integral of. You add 1 to the exponent, you divide by the new exponent, and you get 1.56 joules. So remember, force, the units are newtons. Work, the units are joules if you're in metric. Practice number 3, we have another metric situation here. So practice number 3. A spring has a natural length of 40 centimeters. A 60 Newton force is required to keep it compressed 10 centimeters. How much work is done during this compression? How much work is required to compress the spring to a length of 25 centimeters? So its natural length is 40 centimeters. 60 newtons is required to compress it 1/10 of a meter. So force of 0.1 is equal to 0.1 times the spring constant is equal to 60. So the spring constant is 600. Now we want to know the work done. So we want to compress it 10 centimeters. So we're going from 0 compression to 1/10 of a meter's worth of compression. 600x dx would be 600x squared over 2, evaluated from 0 to 0.1. I did it earlier. It is 3. Okay, then we do it again to see how much work is required to compress the spring to a length of 25. So compressing it 10 took it to 30. Compressing it to 25 would be another 5 centimeters or 0.05 meters. So this work would be equal to, and yeah, it wants the total. So 0 to 0.05 0.15 meters of compression. And again, I did it earlier so you wouldn't have to watch me plug things in. 6.75 Newton meters or joules. So, if the work required to stretch a spring 1 foot beyond its natural length is 12 foot-pounds, how much work is needed to stretch it 9 inches beyond its natural length? Read carefully. The work required is equal to 12 foot-pounds. The other ones gave me the force. This one gave me the work. Work means the integral from and 1 foot beyond its natural length, so 0 to 1. We don't know the spring constant, so we'll just put in K times X dx. Well, I know how to integrate that. This is K times X squared over 2, evaluated from 0 to 1, and luckily it's really easy, so I just have K over 2 times 1 squared minus 0 squared is really just K over 2. And that's equal to 12 foot-pounds. So K is equal to 12 times 2, which is 24. How much work is needed to stretch it 9 inches beyond its natural length? I'm going to go ahead and convert 9 inches, even though I know you've already done it in your head. So 1 foot is equal to 12 inches. So 9 inches is equal to, inches cancels with inches, 9 over 12 feet, which is 3/4 of a foot. I know you did it in your head. You can use a decimal if you want. So work is equal to the integral from 0 to 3/4 of 24x, which is 12x squared, evaluated from 0 to 34. And again, I did it earlier, 6.75 foot-pounds. Okay, now we've got a completely different kind of example. So we're going to take a break from Hooke's Law, and we're going to move on to moving objects that are variable mass. So it's not like the first example where we were just moving a book. Now we have a cable that's going to be heavier the longer it is. It's a 200-pound cable. It's 100 feet long, hanging vertically from the top of a tall building. How much work is required to lift the cable to the top of the building? So we assume that the only acceleration is due to gravity, that there's nothing extra pulling it down. There's no friction that we have to account for. And we assume that the cable is, the weight is evenly distributed. So if we have a 200-pound cable, and it is 100 feet long, then it is 2 pounds per foot. And we're not going to have to account for gravity in here because pounds have gravity already included in there. So there are a couple of ways that you can set this up. One way is to put the positive x-axis pointing downward, and we put the top of the building at the origin. So this is the positive x-axis. X values are getting larger as they go down the building. Advantage, we get to integrate with nice positive x values. So since the weight is equal to 2 pounds per foot, the work is going to be the integral from the bottom to the top, so 0 to 200, 2 times, and when x is equal to 200 down here at the bottom, then we have 2 times 200, the entire weight, 2 times 100, excuse me, down here at the bottom, 100 feet from the top. So when it's down here, the entire weight is on the chain, cable. When it's halfway up, you only have half of the weight. So it's going to be 2x dx. And then it's super easy. X squared from 0 to 200. And I have the answer sitting here, 10,000 foot-pounds. Now, maybe you don't like flipping things upside down. I kind of like having my origin where the origin always is, with the positive x-axis going to the right and the positive y-axis going up. So I would put the top of the cable or the building at 100 and the bottom of the cable at the origin 0, 0. So this would be the point 0, 100 at the top. Still, the weight is 2 pounds per foot because it's the same cable. But now when we think about what we're bringing up, we're still integrating from 0 to 100, and I wrote 200 over here. It was only 100. Because we go from the bottom to the top of the rope. Here we're integrating from 0 to 100. Now when we're here at 0, we have the entire weight of the cable. So it's 2 times 100 minus y. Because when y is 0, the weight is equal to 0. 100 minus 0 times 2. When we get halfway up, then we do 100 minus halfway times 2. So we end up with the same answer. It just looks a little different. And 200y, you would distribute 0 to 100. 200 minus 200 y dy, add 1 to the exponent, divide by the new exponent. I'm not going to write all that down. You still get 10,000 foot-pounds. So either way you want to set it up, integration slightly easier this way. Setting it up and wrapping my head around it. I find slightly easier that way, but whatever works for you. Practice number 5. A 900 kilogram car has gone over a 30-meter cliff. A crane lifts the car with a chain that is 15 kilograms per meter. How much work is done? So take a minute, set this up the way you want to set it up, and we'll meet back here. Remember, it's kilograms, so you have to account for gravity. I did it both ways. I put the origin at the bottom of the cliff, then the distance is 30 minus y. I put the origin at the top of the cliff with the positive x-axis at the bottom where the car is, and then it's just the weight of the car plus 15x, the weight of the chain, because it has to move 300 or 30 feet from the bottom. So either way, you get the exact same answer. I don't care how you set those up. This one's a little more complicated. Now we have a bucket that weighs 4 pounds and a rope of negligible weight. So we're not going to worry about the rope, but we have a bucket of water that is leaky. So we have to account for the water coming out of the bucket. And this one's in pounds, so you don't have to worry about a gravity constant. Give it a try on your own. So I added together the weight of the bucket and the weight of the water, 44 pounds. Then I needed to know how fast I was losing water in pounds per foot, because this representation I have here is feet. So I'm putting the origin at the bottom of the well and the top of the well 80 feet above the bottom. So I'm not interested in seconds, I'm interested in feet. So I'll lose 2 pounds per second, and I'm moving at a rate of 1 second. I move 2 feet, so I can cancel seconds. So 0.2 over 2 is 0.1 pounds per foot of water. So every time I move up a foot, I lose a pound of water. So at the bottom, it weighs 44 pounds. So when y is equal to 0, it weighs 44 pounds. When it moves up, it's going to lose 0.1 every foot that it moves up. So the integral from 0 to 80 of 44 minus 0.1y, and I get 3,200 foot-pounds. So we've done springs, we've done moving chains or objects. Now we're going to find the work that it takes to empty a tank. Here is your procedure, and it's one of the reasons I draw some of my graphs at the origin and integrate with respect to y, because that's what we're going to do with these tank problems. So you draw the y-axis in the vertical direction and choose a convenient origin. Assume the interval a to b corresponds to the vertical extent of the fluid. So we're going to integrate from the bottom of the fluid to the top of the fluid. It may be 0 to something, it may be a negative number to a positive number. Find the cross-sectional area of a horizontal slice and the distance the slice must be lifted. So assume we have a tank that looks like my cup here. We divide it into slices and we calculate the area of each slice. Well, each slice, I'm not going to turn it sideways and show you. Each slice would be a circle in this case, if this were my tank. So we find the area of each slice and then how far each slice has to travel to get to the top of my cup. And that's how we figure out the amount of work it takes. So it's density of the water, or in my case lemonade, times gravity, times the area of a slice, times the distance the slice has to travel, and dy represents the width of the slice, because as always with these Riemann sums and integrals, we think of slicing and then letting the width of the slices decrease, and we end up with an integral. Memorize the density of water because it's easy. It's 1,000 kilograms per cubic meter. Memorize acceleration due to gravity is 9.8 meters per second squared. Let's look at example 5. A tank has the shape of an inverted circular cone with height 10 meters and base radius 4 meters. So inverted, it's upside down like an ice cream cone. It's filled with water to a height of 8 meters. We want to find the work required to empty the tank by pumping all the water to the top of the tank. So first thing I do is draw myself a triangle, because the side of a cone looks like a triangle. Example 5. I'm going to put the center of the bottom of my tank at the origin. I know I have a really pretty picture over there, but I always draw them anyway. Now I'm labeling it. It is 10 meters tall, so this would be the point 0, 10. It's filled with water to a height of 8 meters, so this is the point 0, 8. This is the point, its base radius is 4 meters, so it has 2 meters over here and 2 meters over here, so this is the point 210. And this is the origin, 0, 0. So I got everything labeled for myself. This is a side view. I'm going to need a function to represent this triangle, and actually just a side of this triangle. Because if we look at this tank from the top, this is my side view. I look at it from the top, it's a circle with radius x. But I'm making slices, slice, 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 all along my y-axis. I want to integrate with respect to y. Because my water level is going from 0 to 8. I'm going to be integrating from 0 to 8, and this is meters. So I need a function for x in terms of y. Well, I'm going to use similar triangles. And I'm going to look at just half of the triangle because I really only want to know the radius. So this is going to be equal to 2 because that's the base radius here. And then the height is equal to 10. Every triangle of my x and y coordinates as it's moving up the triangle here, the water level would be x, y. This distance would be x, and this distance would be my y coordinate. So 2 over 10 has to be equal to x over y. So x is equal to 2 over 10, which is 1/5 times y. So this is my radius. So the area of a slice, I'll just call it A as a function of y, is equal to pi r squared. So pi times 1 over 5y squared. So pi over 25 times y squared. So now I have the area of a slice. Let's start talking about the work I'm doing. Well, we know the density of water. I know acceleration due to gravity. I'm going to go from the bottom of the water to the top of the water because that's how long I have stuff to pull out of my tank. So from 0 to 8 because that's where my water level is. But how far does it have to travel? It has to travel all the way to the top of the tank. So I'm going to write down my area, which was 25, pi over 25. Yeah, pi over 25 y squared. Put the right thing in the numerator and the right thing in the denominator. And then the distance is 10 minus y because the bottom part of my lemonade has to travel all the way to the tippy top of the tank. But we're assuming that the straw kind of follows it up, so this top one only has to travel to the top. dy. And now I'm not going to make you watch me do all of that integrating. Oh, I have that wrong. I made it 2. It should have been 4. I didn't read it carefully. No, it says the base radius. Radius is 4 meters. I gave its base diameter 4 meters. So I'm going to go back and fix all those numbers. They are correct here. Be sure you read the problems carefully. We'll do the next one right, I promise. So I went in and fixed everything. It said base radius, not the width of the base, which was how I interpreted it when I did it at first. So let me get rid of those tiny little 2's because it should just be 4. I was given the radius. So that would have been 4 over 10, 2/5. And we end up with, and I write this because it helps me to remember it, rho times g, density times gravity, area of a slice times the distance. Practice number 7. We've got another tank. Now, this one you're going to have a triangle from the side, but instead of a circle from your top view, you've got a rectangle for your top view. So it's going to be a little easier. So take a minute, work on this one. We'll meet back and I'll be sure I have it right. So how'd this one go? Didn't have a pi in it, so it was even easier to integrate. Well, the pi just made the number more complicated. So first thing I did was draw my side view. I put my origin at the bottom of the tank. And again, it looked like a triangle from the side. And it has its little spout above the water level. And then the top view was a rectangle. It's 2x wide and 8 units deep. So 2x times 8 would be the area of a slice. I needed to write that with y's in it. So I did the similar triangle method here. Some students don't like the similar triangle method. So I did the equation of a line method also. So I took the slope from this point to this point, changes in the y divided by changes in the x is equal to 2. And then I chose the origin as my point because that's easy. Y minus my y coordinate is equal to slope times x minus my x coordinate. So y is 2x, so x is y over 2. You can do it either way. You don't have to do it both ways. I just did that for illustration purposes. So 16 times y over 2 is 8y. The water's going from 0 to 3. It has to travel up to the top of the spout, so it has to get all the way up to 5. So rho times g times area times distance times the thickness of a slice gives me about 10 million joules. Let's do a tank that is filled with water, and we're going to assume water weighs 62.5 pounds per cubic foot. Sometimes you'll see it as 62.4 pounds per cubic foot. I will give you the density of water in pounds per cubic foot if you need it on test day. So this one, I'm going to set it up a little differently. So we'll do this one together, and then I'll let you do the next one. Of course, you can stop the video whenever you want and do them all on your own. I'm going to put not the center at the origin, but this bottom of the tank right here at the origin. So it is 6 feet tall. Now its top view is going to be a rectangle, and it is 10 feet deep, and this is 12 feet. So 12 feet and 6 feet. The top view is a rectangle, which is 10 feet deep, and it's going to be x units wide, not 2x this time, because we have a right triangle that's living on one side of the y-axis. So here I'm going to once again draw my similar triangle. 12 and 6, the water level is going up, and yeah, the spout's just at the top here. So the water level and the distance are going to be the same because we just have to get to the top of the tank. This is x, this is y. So 12 over 6 is equal to x over y. So x is equal to 2y. So since area is equal to 10x, it's equal to 10 times 2y. It's 20y. We just talked about the water level and the distance. Water level is 6 feet. So 0 to 6, and distance. Zero to 6, and I'm going to write this as 0 to 6 because I like to represent my limits of integration are the water level. Distance is what gives me my 6 minus y, not y minus 6. Because when y is equal to 0, it has to move 6 feet. When y is equal to 3, it has to move 3 minus 6, or 3 feet. So work is equal to integral from 0 to 6, rho times g. Now remember, this is U.S. customary units, so the g is already embedded in the 62.5 pounds per cubic foot because pounds includes gravity. So 62.5 area was 20y, and distance is 6 minus y dy. I have the answer written down over here. And I get 45,000 foot-pounds. So that was a nice simple one. Number 9, we have a trough. A trough, in case you don't know what it is, it's something that animals drink of. It's just a container for water. It has a trapezoidal cross section. So draw your trapezoid on with the center of the bottom at the origin, and then it is 12 meters long. So you'll use that to find your rectangular top view. Alrighty. I use similar triangles again to find my equation for y, or x in terms of y. The top view was a rectangle. Again, the width of the rectangle is 2x, and the depth is the length of the trough, which is 12 meters. It was 3 meters wide at the base, so 1.5 and 1.5. And it was 5 meters tall, 6 meters wide at the top, so 3 and 3. I also went ahead and plotted my points, and I found the equation for x in terms of y using the equation of a line as well. So I'll show you that in a moment. But we have 1.5 over 5 because this triangle just lives right over here, so it's 3 minus 1.5, which is x minus 1.5. So x minus 1.5 is at the top of the similar triangle, and then the height of the triangle is still y, or 5. So I set up that proportion, and then I got 0.3y plus 1.5, and then I multiplied to end up with 7.2y plus 36. I also did it using slope is equal to the change in the y divided by the change in the x, and then I used this point, so y minus my y coordinate and x minus my x coordinate, and then solved for x, and got the exact same thing. The water is going from the bottom to the top of the trough, and it's 5 meters tall. The distance it has to travel is to the top of the trough, 5 meters tall. Rho times g, area, distance, 5,880,000 joules. One more. This time we have a conical tank filled with salad oil. So, top view is going to be a circle, side view is going to be a triangle. You can do it. Give it a try. It's a lot like the first one we did because it's another conical tank. And we ended up again with x being half of y. So I plugged in pi times x squared for pi equals y over 2 squared. So I got pi over 4 times y squared for my area. The oil goes up to 8 feet because it says that there's 2 feet from the top of the tank to the top of the oil. So 10 minus 2 gave me 8. The distance it has to travel is all the way to the top of the tank. So 10 minus y. And again, this one has feet, so it's U.S. customary units. You don't have to add in anything for gravity. It's included in the pounds. So 57 pounds per cubic foot. So I came up with 9728 pi, so about 30,000 foot-pounds. You can do it. Hardest part's finding that equation for the area of your slice, but you can do it. Just practice.